Okay, let's just dive right into this explainer. Today, we're looking at the completely fascinating journey of artificial intelligence, going all the way from basic lines of code to actual real-world physical systems. We hear the term AI literally everywhere today, but when you look at the foundational research and where this technology is actually heading, wow, it reveals a story that is way more complex and, honestly, way more thrilling than you might expect. So we're going to trace that exact path from the earliest computer algorithms right up to fully autonomous robots and synthetic companions.
But before we get into the nuts and bolts, I want you to consider this for a second. Will machines ever truly achieve human traits? Things like emotion, consciousness, or even free will? Now I know, that sounds exactly like a sci-fi movie. But as we unpack the current state of engineering and computer science today, you'll see that scientists are actively blazing a trail toward that exact future.
So, to understand where we're going, we really need to set our baseline. What is AI? Well, at its absolute core, artificial intelligence is the capability of a computational system to perform tasks that we usually associate with human intelligence. We're talking about perception, learning, reasoning, making decisions, the whole shebang. Researchers basically use methods rooted in formal logic, statistics, and artificial neural networks to create software that can perceive its environment and then take actions to maximize its chances of hitting a specific goal.
And to fully grasp how we got here, we have to look at this monumental shift from early, super rigid programming to the dynamic, self-teaching models driving today's tech. See, early AI relied heavily on classical algorithms. These were inflexible, completely static sets of rules where engineers basically had to hand code every single step. But as you can probably guess, that approach completely falls apart when faced with the unpredictability of the real world. Enter machine learning. It's a real game changer. Instead of static rules, machine learning allows computers to actually absorb data from interacting with the world and then literally rewrite their own programming. They get smarter entirely on their own through experience.
Section 1. Navigating the physical world.
Okay, so the clearest road to this physical future is for sure the self-driving car. So how exactly does an autonomous vehicle mimic human decision-making? Well, it relies on this incredibly cool combination of memory and immediate visual perception. The AI software starts with an internal, static 3D map of the infrastructure, streets, stop signs, that kind of thing. But then, it overlays that map with dynamic, real-time data gathered from cameras and advanced radar. It's constantly computing moving traffic, pedestrians, sudden obstacles, basically objectively understanding exactly where it is in space so it can make those complex decisions completely on the fly.
Now imagine being stranded in a pitch-black, completely unmapped coal mine. Sounds terrifying, right? Well, the DARPA rescue robot R2 operates totally autonomously to come find you. First, it literally drops Wi-Fi repeaters like breadcrumbs just to establish a network. Then, it uses LiDAR, which means it shoots out these laser pulses of light that bounce back off solid objects to generate a 3D map of its environment totally from scratch. Finally, it uses visual data to recognize and pinpoint its target, deciding 100% on its own where it needs to explore next.
And think about this. A 3-month-old baby cognitively maps out her surroundings and learns to recognize objects just through trial and error, right? Well, this robot is doing the exact same thing down in that coal mine. It explores, it hits a dead end, it turns around, and then it dynamically rewrites its own understanding of the space. It's wild.
But moving from the ground up into the air, that requires a massive leap in processing power. See, while cars operate mostly on a 2D plane, an autonomous aerial drone has to navigate unmapped, three-dimensional spaces. And they do this without GPS. Instead, these drones use a gimbaled LiDAR system to essentially paint a full 360-degree sphere right around themselves. They calculate what engineers call voxels. You can think of voxels as basically 3D cubes of space. The drone is constantly calculating to figure out, hey, is this cube occupied by an obstacle, or is it free space that I can safely fly through?
Section 2. Swarm intelligence and teamwork. So, what happens when these robots start working together? When they swarm, they unlock some truly massive advantages. Researchers are actually mimicking nature here. Think of a flock of birds or a busy colony of ants to coordinate groups of small drones. Using their onboard cameras and these bio-inspired algorithms, they establish a localized network to figure out exactly where they are in relation to one another. And because they work in parallel, they can map out spaces incredibly fast. The end goal for this tech even includes precision agriculture. We're talking about deploying swarms of robotic bees to organically and efficiently pollinate crops. To put that into perspective, this could be absolutely vital for feeding a global population of 9 billion people in the coming decades. It really shows how these advancements hit super close to home.
Section 3. Collaborating with humans.
Okay, so the machines can work with each other.
But let's talk about how they integrate into human teams. MIT researchers recently made this brilliant breakthrough in human-robot collaboration. Look at it this way. If you teach a robot the direct, rigid mathematical sequence of setting a dinner table, it completely fails if you just hide the spoon. It doesn't know what to do. But if a robot observes a human setting a table over and over again, the machine learning software actually grasps the bigger picture context. It learns the concept of the task. So when those researchers hid the spoon and then suddenly revealed it, the robot dynamically adapted. It instantly grabbed the spoon and placed it exactly where it belonged. It wasn't just following a mindless script anymore, it was demonstrating a real, general understanding. But as you know, true teamwork requires predicting the future. In industrial settings, AI is now actually learning to anticipate human behavior based on really subtle contextual cues. For example, while a human worker places fasteners on an airplane surface, a robotic arm right next to them, applying sealant, is actively tracking the human's movements. The robot predicts exactly where the human's hand is going to go next and calculates a roundabout path for itself to actively avoid collisions. This totally transforms the robot from a dangerous, heavy machine that has to be locked in a cage into a seamless, highly collaborative teammate.
Section 4. The Quest for Self-Awareness.
Now we arrive at a frontier that honestly feels like pure science fiction, giving these machines a sense of self. Dr. Hod Lipson beautifully demystifies a highly philosophical concept here. He frames consciousness simply as an internal software simulation. Basically, before a machine can have abstract thoughts, it must first be able to simulate its physical self. It literally has to generate an internal self-image right within its computer mind.
What's fascinating is that engineers are now programming a biological concept called proprioception directly into robot limbs. Proprioception is basically that sixth sense that lets you touch your nose even when your eyes are closed. You just naturally have an internal model of your body's position in space. Well, by programming robots to understand their own physical boundaries, researchers are taking the absolute first steps toward genuine robotic self-awareness.
And that brings us to this incredible real-world test. Researchers literally built a robotic arm with no cameras at all, so effectively it was blindfolded. Through unsupervised trial and error, acting a lot like a babbling baby flailing its arms around to figure out its limits, the robot built an internal map of itself and its environment. Relying purely on that internal proprioceptive model, the arm was able to successfully locate and pick up cotton balls in the real world. It completely bridged the gap between its digital self-image and physical reality. How cool is that?
So building a complete synthetic companion basically happens in three phases. First, it starts with natural language processing. This is moving way beyond rigid voice commands to the AI actually understanding human context and tone of voice. Next, we have software generating these hyper-realistic virtual avatars in real time, literally matching expressions on the fly. And finally, all these elements are placed into physical androids. These are silicone robots equipped with advanced vision systems that can actually detect your emotions just by reading your facial expressions and your skin temperature. It allows for completely natural, dynamic face-to-face communication.
Now, of course, seeing these physical androids and hyper-intelligent robots inevitably brings up the million-dollar question: what about human labor? It's a huge topic of discussion. But here's the thing. According to the source data, while certain repetitive or super dangerous tasks are definitely going to be automated, the AI sector is actually expected to generate 58 million brand new types of jobs globally in just the next few years. To put that into perspective, it's a massive shift in how humanity will spend its working hours. We'll be transitioning away from tedious, repetitive tasks and moving much more toward overseeing and collaborating with these AI systems.
Section 5. Ethics of Hyperintelligence. As these systems escalate in capability, we have to look impartially at the massive ethical hurdles they present. Consider this very real programmatic reality. If an autonomous vehicle has to choose between hitting a jaywalker or swerving into oncoming traffic to save that pedestrian but potentially killing its own passenger, what code do you write? This isn't theoretical. It's inspired by a tragic, real-world accident in Arizona where an autonomous vehicle struck a pedestrian it just couldn't properly identify. Engineers are now literally forced to program these life-or-death decisions. It is a staggering programmatic challenge.
And the ethical challenges extend way beyond just autonomous vehicles. We are facing multi-layered risks here. You've got algorithmic bias, where human prejudices are accidentally baked right into the code. Then there's the severe threat of deepfakes, these digital fabrications that can literally hijack a person's physical identity. There's also the stark reality that bad actors could weaponize those autonomous drone swarms we talked about earlier.
And as these systems inch closer to artificial general intelligence, researchers are actively debating the long-term existential risks to humanity itself. This is the definition of a dual-use technology. It carries incredible promise, but also significant peril.
Which brings us to our final thought for this explainer. We have seen how these machines have evolved from rigid, inflexible algorithms into dynamic learners. They are navigating our world, they're anticipating our needs, and they're even beginning to simulate a sense of self-awareness. But as we stand right on the brink of creating entities that could very well surpass human intelligence, we have to ask a tough question. Will a true partnership with hyper-intelligent machines ultimately transform humanity for the greater good? Honestly, these are the ultimate stakes of the AI revolution, and it's a future we're all going to have to navigate together.